poster with like the sun and all the heads and the chains that they have. We got a really good picture from that, but like, I would absolutely create one of these beautiful hunting rifle stone exaggeration, but that's like that.
A war crime.
That's not even like the. It's not a war crime.
If you steal something, yeah, it's a war crime.
If you're taking weapons away, that's not a war crime.
No, if you're taking it for yourself, yes.
That's fine, but the bigger issue is that like that's taking that into Israel is just like that's illegal. It's a non-legal weapon, and people have gotten caught for it, gotten bent over the barrel.
Okay, so welcome back to linear algebra. Full screen. Hide video panel. And let me remind you what happened to last time. And we defined what a field is. A field is a set of elements which we call scalars or numbers. I'm scrolling towards it. Along with two, here it is. Along with two operations, addition and multiplication, such that the 7 following properties hold, things we expect ways we sum of the product of two numbers is the number, the multiplication and addition are commutative, and
Then
Got it.
Associative law, it does if I do the same operation, if I do the same operation twice, and the order of the parentheses does not matter. There are neutral numbers. 0 is neutral for addition, and 1 is neutral for multiplication, and they are different from one another. So by this property, a field of numbers must have at least 2 elements, because it must have a 0 and it must have a 1, and they must be different than one another. And every number should have a negative counterpart. Every number other than 0 has to have an inverse one. And lastly, the distribution law, A times B plus C is AB plus AC. So every field of numbers must hold these 7 properties. And we use that to create a new field, which is the complex numbers field. That one, which we define by taking every number, every complex number is a point on the complex plane. We defined operations of addition and multiplication. We proved that it is a field, and we've seen that the x-axis, the real axis, behaves just like the real numbers. So we assume that the real numbers are a part of the complex numbers. Here it is, and we've seen a certain unique number, special number I, the 0.01, which is true for that I squared equals -1. That's where all the hype is with the complex numbers. And that's it. And basically, and lastly, we've seen that we don't have to remember the convoluted operations, because the point AB is equal to the real number A plus the real number B times I. So now we can work with the complex numbers just as A plus BI, and all we need to remember is that I squared is equal -1 as such, right? I use the distribution law, and I calculate the multiplication this way, and I don't need to remember the AC minus BD and so forth. I can calculate it myself. A few more things, this is all part of the recap. And the real part of a complex number is the x value is the a, and the imaginary part is the y value is the b. And for every complex number, its a complex conjugate is a minus bi. Their multiplication is almost 1. That's why we use it as an inverse. And I think that's about it with the recap. Just did I write the absolute value of a complex number?
I don't think we did.
No, so I'll do that. Okay. So I should have done it along with the real and the imaginary part, so it's not, I don't know, it's not fluent with today's lecture, but it's not a hard concept.
We won't care if you put it before lecture 2, it's fine.
Yeah.
We cite in the
You agree,
practice.
Thomas?
We
Yes.
cite in the practice, so.
Yeah. No, it's not that surprising, but I think like where it should be next to these guys. Okay, so all right, and the absolute value of z, the absolute value of a plus bi is the square root of a squared plus b squared. Okay. Okay, great. I added it here. I will speak about it in 2 seconds anyway, but in another manner. So, I finished last lecture with saying this is the algebraic window into the complex numbers, because I've presented to you the complex numbers with the I don't know, stale definition. In Hebrew you say yavesh. Stale, I think it's even better, but with a stale definition of operations and multiplications and their properties, with not much, I don't know, meaning behind it. The concept of meaning for students usually means geometry. But now we will see the complex numbers, the same complex numbers. It's not a new subject. These are the same numbers with the same operations, but now we will look at them geometrically. Now we will study the complex numbers geometrically. And a natural question is why? We already seen them. We supposedly understood what I said. Why do we need to look at the same subject from another point of view? So I'm asking you that for I don't know, a couple of minutes. Why should we learn the same subject twice from 2 different points of views? Why should we do it? Yes.
Because humans are great at visualizing things, and when you have something you can visualize, you can understand it.
Okay. So you say that's a valid answer. You say geometrically will help me visualize, but then I will counter with, okay, so why didn't we just learn it geometrically?
Because learning it geometric, you need both, because the
Why?
because the actual hard facts and the calculations are what you do and give you exact results. Whereas
So you say
geometric,
the algebraic part is easy to calculate, the geometric part is easy to envision. Generally, you're correct. Here it's there is an even I wouldn't say better question because answer, because what you said is part of the answer, but there are more answers, I would say. But I really agree with most what you said. Yes, Thomas.
We can use the same thing for different uses, and maybe one use is more as a vector, and some other uses the geometrical part better.
Okay, so for uses that are more geometrical, the geometric point of view is easier. I don't think that's actually true. Maybe a part of it, but still not the full answer. What else? So in general, and why do I'll keep heading at this point because it's important in general. You guys are going to be programmers. Why does there need to be more than one? You're surprised, you didn't know that. Why is there more than one programming language?
Because people are annoying and like different tools for the same job.
Not because people are annoying.
Optimization.
It might be true, but it's not the reason. Different points of view, not only do they allow you to solve different problems more naturally, and that's what will occur here, and you will see. Using the algebraic problems, some of them it's easy to solve using the algebraic notation, and some of them are actually easier to solve using the geometric notation. So some of the time we actually are able to solve different questions using the different point of views. But more than that, and that is a high mathematical truth, when looking at the problem from a different point of view, sometimes we understand it better and we are actually able to solve it. Calculus was invented by Newton Leibniz in the 17th century with the same tools Euclid had at 300 BC. So how come Newton Leibniz got so far ahead so quickly when about 2000 years, humanity hasn't budged? Because they thought of a new language. They found the right point of view to look at problems, and suddenly, boom, there was explosion of, and calculus was invented, this explosion of data. So sometimes it's, and for programming as well, sometimes when you look at a problem using a certain language, you see, I don't know, object-oriented. Have you started learning object-oriented? When you think about a programming problem in an object-oriented orientation, you sometimes solve it much, much better than just function and loops and whatnot. Okay, and so that was I don't know, 5 minutes monologue, but I think it's important in general because what you do in your bachelor degree is not studying how to derive functions or I don't know, solve linear system of equations. You're supposed to enhance your way of thinking, and I think, for me at least, but that's the most important part of the whole thing, is understanding different point of views and be able to use them much more than just solving dry mathematical problems. So after that monologue, and we will study the complex numbers geometrically. Each complex number z equals a plus bi equals ab is a point on the complex plane, and we can and has and is defined by its distance from the origin 0, 0, which is the complex number 0. And what else? It's not enough to know what's the distance. What else? And its angle. And in its angle. So that would be the geometric notation. So let's start with a simple example. If we take the number, if we take the number 1 plus I, what is its distance? And this distance from the origin, what is it?
The square root of 2.
Is the absolute value of z which is the square root of 1 squared plus 1 squared, which is the square root of 2 due to Pythagoras. Agreed?
Or-
Agreed?
How did you say it? Pythagoras?
Pythagoras, I don't know, I say it in Hebrew. And how do you say it in English?
Pythagoras.
Pythagoras.
No,
I
you
said,
don't.
I
Yes, I
said
do.
Pythagoras. Okay.
Maybe in downtown England.
Excuse me.
They told me I should teach in English the word specific.
Yeah, what accent?
Yeah. I can speak Scottish. Milk. Okay, right. I'm not good at accents. Just a quick thing. My sister is an Israeli. She married a British guy, and she did her postdoc in the U.S. So her daughter was American. So first of all, for this short amount of time, there were 3 different citizenship altogether, and then they moved to Scotland. So her child had a strong Scottish accent for a while, and now they're all British.
I can't
Okay.
imagine that sounds too good speaking in Hebrew.
Yeah, and they always laugh. Yeah, they always laugh at our accent and our Pythagoras. Okay. Yes, she does speak Hebrew fluently, actually, the child. Okay, in any case, that's the distance from the origin. Let's draw it a second so you see the angle quite easily. Later we will learn how to calculate it, but now I just wish for you to see it. So the point is 1, 1. Let's connect it, segment. Let's connect it to the origin, and the angle I speak about is the angle towards the positive side of the real axis. So this is this angle, and what is this angle?
Square root of 2.
The angle is not a square root of 2.
The angle, sorry, 45.
5.
Yeah, 45 degrees or pi over 4 radians, which we will use. And well, that's huge.
Can you explain why why the distance from the origin is absolute everything what you wrote? Can you explain that?
I'll do it in a second in general, but that's Pythagoras theorem, right? The triangle you see here has that's the hypotenuse, and that's the edge.
Side. Side.
Doesn't have in Hebrew it has a
Adjacent.
special yeah, no, but in Hebrew it has a special name, nitzavim. So the edges that are not the hypotenuse are 1 and 1.
Right. Okay.
And then Pythagoras says 1 squared plus 1 squared equals the
C squared.
c squared, yeah, hypotenuse squared. So
Okay.
from there. We'll do it again in a few seconds. That's just the first example for you to see what I mean. And the angle, let's call it theta, is pi over 4, which is 45 degrees. And we'll use radians, especially in calculus, and we'll explain why. Here it doesn't, in linear algebra, it doesn't really matter. And anyone can see. So the geometrical way of looking at the number is remembering its distance from the origin and its angle towards the positive part of the real axis, real line. So our first technical question will be how to convert from the algebraic notation to the geometric one and vice versa. So we're not sure why we're doing that, but I gave you a long monologue about it. So now I'm just speaking about the technical ability that when given the algebraic notation, like here, 1 plus I, you know that the geometrical one is square root of 2 and pi over 4. We also have a way to write it, but I'm holding that back for a few seconds. And vice versa, if you have the distance and the angle, you wish to find A and B. Okay, so let's start. Which one do you think is it's easier, from the algebraic to the geometric, or from the geometric to the algebraic?
Algebraic to geometric.
The opposite.
The opposite.
Yeah, but always students always answer the opposite, so it's not 50-50. You're always wrong. I'm not sure
how
why.
to transform?
It's much easier from the geometric to the algebraic. You'll see in a second.
Sure.
You'll see in a second.
Yeah.
I don't know why. Students always.
I thought it was like you have to do the sine of the angle times the length, and that's
Yeah. Yes, that's from the geometric to the algebraic.
yeah, that's not easier.
That's easier. From the algebraic to the geometric, you have to find the angle.
You have to find the angle.
Yes, that's easier. That's a formula. It doesn't really matter, right? But I don't know. Okay, so assume we have a complex number with a distance, which we'll call r, and angle, which we'll call theta. And we wish to find A and B. Okay, so let's go to the drawing board and write that the point AB is actually the complex number A plus BI. And that is what we wish to find, the A and the B. And what do we have? What are data? Netunim. How do you say netunim?
That data,
Data?
נתונים בעצם כוונה.
In the question, you have the netunim of the question and what you need to solve.
Given
Data, and there is no special word in Hebrew. It's all netunim. It's the data, right? But it feels not natural for me to simply say data. In any case, we have the data, the netunim, which are the length of the hypotenuse, which is r, and the angle, which is theta. So we theta. That's what I wanted. Okay. So let's look at the triangle segment. I need to put B. B is 1, 0 here. Segment OB, segment BA. Let's make them dotted or dashed, to be exact. What is the length of the edges? So what is the length of this edge? Included in GeoGebra, it's 1, but I mean in general. Think of it as a general example. So this is AB. What would be the length here? B. So that's B. Okay. And the length of the other edge? Yeah, adjacent is A, adjacent and opposite. Oh, I forgot to copy it. So this is B again, right? And now a bit of trigonometry. The SOHCAHTOA, do you know SOHCAHTOA, right?
Mm.
The opposite over the hypotenuse equals to the sine of the angle. So P over, remember, so TOA, right? Yes. And sine is opposite over the hypotenuse. Cosine is adjacent over the hypotenuse, and tan and tangent is the opposite over the adjacent. Okay, great. So the sine of theta equals to b over r. So b, and that's what we wish to find, is r times the sine of theta. So that's an easy formula, okay? And similarly, the cosine of theta is the adjacent over the hypotenuse, and that's why a equals r times the cosine of theta, okay? So the complex number is equal to um
Cosine theta and sine theta.
no, r cosine of theta plus I r sine of theta, which is equal to r times cosine of theta plus I times sine of theta, which we call, what we call the cosine of theta plus I sine of theta? Cis of theta. Do you know this notation?
No.
Okay, so it's a shorthand for cosine I sine, right? CIS, the I is the, so that's a definition. When you see cis of theta, it means the cosine of theta plus I sine of theta. It's a shorthand, nothing more than that. And maybe I'm not sure if you're familiar or not, it's actually equals to e to the power of I theta. So this is just a notation. Notation. This is actually a mathematical truth, but true, but we won't cover it in our courses, just for your general knowledge. And did you wish to ask something?
Yeah, I was gonna ask why do we have r cis theta when we can just write r e to the I?
E to the I of theta, yeah, because it's not clear at all why e to the I of theta is cosinus theta plus I sinus theta. It's actually true, but it's not clear. And cis helps us remember the formula because it's actually written there as a shorthand. Yeah.
If I already know it, can I write it anyway?
Yeah, of course.
Okay.
Yeah, that's a cultural thing. In Israel, many years ago, they used this notation, but since then we use this notation. Students are very surprised to see this, and this everyone knows. But it really doesn't matter, right? It's just a shorthand. It's important that you know. So given, so for the example above, it's not exactly so. So example, given the number 1 plus I, we said that the distance is the square root of 2, and the angle was pi over 4. So that's the way we write the geometric version of the complex number. And like you said, it's the square root of 2 times e to the power of I pi over 4. It's the same, okay? So this is the geometrical notation, or this one is, whichever you prefer, and this is the algebraic notation. And given the geometric one, it's quite easy to get the algebraic one. Let's see another example, which we actually do it. So example, and I changed the shorthand for example each time. And say we have, I don't know, this square, not square, 2 times the cis of pi over 6. Okay, so we might be able to imagine geometrically where is this number. Its length is 2, the angle is pi over 6, 30 degrees. So it's somewhere over there. We'll put it on the axis, on the plane. So it would be, I don't know, something like here, more or less, right? But how do I actually find the A and B? The imaginary part, the real part, the algebraic notation of the number. So the following formula does it quite easily. It says that it's 2 times the cosine of pi over 6 plus I times 2 times the sine of pi over 6. And then we use calculator to find out these numbers, and I'll do it using the Wolfram.
Are we supposed to remember?
No, you use the calculator in the test. You don't need to remember all the sine and cosine of every special angle. Okay, so it's the square root of 3 plus I. So it's the square root of 3 plus I. And I'll show you on the plane. Let's draw up square root of 3. Square root of 3 plus comma 1. That's the point. Segment OC. And now I will write angle of the segment. It did not like that. I write angle of C, I think it will, yes. And you see that the angle here is 30 degrees, pi over 6, exactly what we expected to happen. Okay, so we actually did something. The length, by the way, it's also written here. So the length of this edge is 2. Its angle is 30, and its algebraic notation is square root of 3 comma 1. And that's exactly what we find without too much work. Okay, note that I only showed you this story at the first quarter. Something like that. It's a quarter of the plane where x and y are positive. What about the rest of the plane? Luckily, the same formula is true at every other point of the plane. You can take it as an exercise to prove, but it's definitely not a triangle anymore, because think about the angles. The angles over 90 degrees are not an angle of a triangle anymore. But still, the same formula of A equals R cosine of theta and B equals R sine of theta works everywhere on the plane, and we use them everywhere. So we locked out on this one, but we use it. Next, now vice versa. Now given an algebraic notation such as square root of 3 plus I, we wish to find the geometric or polar, does it has another name? In Hebrew, it's kotvi, which is polar, or polar, which is polar. We say it in both, yeah. So in the Hebrew translation or in the English version. So in geometric or polar notation of the number. So we obviously know the answer because a few seconds ago we started with the geometric one and we moved to the algebraic one, but we want to know how to do it in general, right? So let's get back to this drawing. And now what is the data that is given and what are the values which we need to find? What is given now?
A and B.
A and B, right? I assume that I was given the algebraic notation and I wish to find the geometric notation, which means what do I need to find?
The angle.
The angle and the distance there, right? So now that's what I promised you before. Now I'll write the general formula for R due to Pythagoras. So you look at this triangle A, B, and R. So due to Pythagoras, let's say Pythagoras. Due to Pythagoras, a squared plus b squared equals r squared, and therefore r is the square root of a squared plus b squared, which is the absolute value of z, right? So getting the r is just as easy. It's not, the angle is the only problematic part of the whole thing, okay? So in our example, the number is the square root of 3 plus 1 times I. So if I square the square root of 3, it's 3, plus 1 is 4, the square root of 4 is 2. That's the actual distance, and that's what we saw. What about the angle? How can I find the angle given A and B?
The cosine rule?
So theoretically, you can find R and use it. It's not the best method. How can you find theta straight from A and B without calculating the R first? The tangent, exactly. So the tangent of the angle is the opposite over the adjacent. Agreed? So theta is supposedly the arctan, the inverse function of tan of B over A. Supposedly. Supposedly.
So the
Close enough, right?
They all,
the U and the O is swapped.
they always, yeah.
The L is double?
No, the O and the U, you swap it.
SUP.
Suppose.
Yeah.
Supposedly. Fine? Okay.
Supposedly.
Supposedly. Yeah, I suppose. I don't suppose. I agree. I agree. I never suppose. Okay. Supposedly. So, and why do I say supposedly? However, arctan only
Works on
returns values between in the first and the fourth, between negative 90 degrees, minus pi over 2, pi over 2. Okay. So we miss each complex number in the second and third quadrants of the plane.
So this only works for complex numbers with positive reals.
Yes.
Uh,
So plain, like this,
yeah.
right? Not simple. So
it's-
so how do we fix the problem? We notice that for a plus bi and for minus a plus bi, the quotient b over a equals minus b over minus a. Do you agree with that claim? What does it mean about the angle? What is the angle between z and minus z?
Oh, fine.
Pi. And the angle between z and minus z is pi. So in these cases, the actual angle is the arctan of b over a plus pi. So it's the angle of z plus pi that takes us to negative z, to the right place that we are supposed to be at. And lastly, how do we know if the complex number is within the first and fourth quadrants, or in the second and the third?
because the real
Because the real part, the way to distinguish between the two cases is whether A is positive positive number, and therefore the angle is just the arctan of 1 over square root of 3, which is pi over 6. Make sure of that. That's true because I started from pi over 6, but let's just make sure. Yay, pi over 6. Okay. Now, if the number was its negative complex number, meaning if z is minus the square root of 3 minus I, what do you expect the angle to be? Let's look at it for a second before we'll calculate it. So this is square root of 3 comma 1. Right. So this is square root of 3 comma 1, which is the square root of 3 plus I. And its negative counterpart is minus, where is it? What is the angle
from
Wait, I need to just a second. I don't need A anymore, or this, or this, or that, or that, or this, or that, or this, or that, or this. Great. Okay, now we have a nice screen which we can understand something from. So the number, the complex number, square root of 3 plus I is that point of, let's take this and make it into a distance, and the distance was 2, okay? So now I'm asking about the minus this number, which means minus square root of 3 minus I, and I ask what is its angle, but the angle okay, we're back.
Basically that it's exactly the same, but you also have to add the 180.
Exactly. So angle D, just as you say, it said is 210, okay, which is 30 plus 180. But and I will write it. And how do we know it by calculation, not using the drawing? We say the real part, first of all, that's minus Z, sorry. The real part of minus Z is negative square root of 3, which is smaller than 0. And therefore, the angle of this number is the arctan of -1 over -1 over minus the square root of 3 plus pi. And the way we knew that there is a plus pi here is because the real part of the number was negative. That's exactly when we add pi. If the real part is positive, we don't add the pi. That's the whole thing. So it's a bit more complex, and the formulas are harder to remember than the other way around, but still not too complex. It's quite easy to do. And that's true, and I'm adding the drawing as well.
So what you're saying is that the complicated part is the second quadrant.
Yeah, second, but also remember the arctan of B over A, and like because of the R cosine and R sine are so in Israel, like I said, the cis, it's within the shorthand of deriving, and we use it much more, and everyone remembers it. And the arctan of B over A, people don't remember, and they also forget to add the pi. But that's not mathematical. It's not a mathematical fact. It's just fact about people. I don't know. They usually forget that part and not the other one. So now we know how to convert from the geometrical notation to algebraic one, and from the algebraic notation to the geometrical one. And we are remained with the question as to why should we do all that. But just to be sure, I will give you another example before. Take the number minus 3i. What is its geometrical notation? So what is the distance of minus 3i from the origin?
Root of 3.
No, it's just 3. Right?
Right.
3i is 0 minus 3. It's just 3 steps away from the origin. What is its angle?
Minus 5.
Yeah, exactly. Minus pi over 2. And in this case, the A is equals 0. So you can't even use the arctan of B over A. But it's easy just to think about the plane. Where is minus 3i located at the plane? So it's, like I said, 0 minus 3. It is simply that point here. And its distance is 3. That's the square root of 3 squared, of minus 3 squared. And its angle is negative pi over 2, or 3 times pi over 2. That's the same. You can use whichever. Do you have any questions so far? So now I have a question.
Why is minus 3 for minus 3i? Why is R 3?
And
Did we
so,
have our
first of all, when you look at the drawing, do you agree the distance from here to here is 3? So that's one explanation. The more algebraic explanation is that R is the square root
right
of 0 squared plus
because we don't
minus
saying, okay,
3.
that is our B and we don't have the A.
The A is
We
0.
only
Yeah.
have B. Okay.
Yeah, yeah. There is no, we don't have it. It could be possibly 0. Every complex number is a point on the plane. Okay. And that's also an interesting question, because the way I reminded you of the distance formula is using Pythagoras theorem. Here Pythagoras doesn't hold. Distance between two numbers on the same line, on the same straight line, well, on the same axis, does not create a triangle at all. So it's just the subtraction between them. Okay. But the formula holds. The R formula always holds. The angles had, like you see now, 3 cases. A being positive, A being negative, and A being 0. Okay, yes.
What do you mean when you say Pythagoras doesn't hold here?
If I'll try to, there is no triangle. Look at the drawing. Where this is the point. For which triangle you use Pythagoras theorem. It's not that the Pythagoras theorem is false when I'm saying it doesn't hold. It's not relevant, maybe, right? There is no triangle at all. So the proof of distance using Pythagoras is false. It is false. You can't say it's a triangle with the edge of length 0. That's completely false. That is literally not a triangle.
Because a triangle
It has 2 angles, not 3 angles. It's literally not a
Well,
triangle.
what if the triangle was just in 3D space?
And
And we were looking at it from a 1D perspective. Or a 2D perspective.
still, I don't see 3 points here. I don't see 3 points here. I don't see any way, because look, the formula itself is 0 squared plus negative 3 squared. These are not the length of edges of a triangle, because 0 is not the length of an edge. I don't care what is the dimension. I don't see how can that be a triangle. doesn't really matter, but it's something I noticed because I always taught and said that the formula for distance is due to Pythagoras. That's what is known. Apart from the two problematic situations where the 2 points are on the same axis, either on the same x-axis or the y-axis, then it's not Pythagoras. It's still true, and the formula still holds, so we don't really care. Okay.
Isn't just the x-axis or the y-axis. Any,
Yeah.
any.
When they are on a line parallel, on a line parallel to either of the axes, you're correct. Okay, it doesn't really matter. It's just a small thing I noticed while teaching a few years back. Okay, so I said I have another question. So question. How much is 1 plus I times, I don't know, 1, 2, 3? What would you do if I asked you to calculate 1 plus I to the power of 123?
Use the binomial.
That's horrible, right?
Yeah.
I don't recommend it. By the way, it's also interesting from a computer science point of view. If I'll ask you to program a program that's to write a program that calculates it, what will be its complexity? How many steps will you take in order to calculate that?
2 to the n or something?
So you assume 122. Let's just say multiplication, right? You will be wrong. Well, you could do that, but you could also do, that's a bit of general knowledge, to be honest, but it's interesting, I think. You can square 1 over I, right? That's one operation. Now you can square it. What power do you get? 4. Square it. What do you get?
8.
8. How many times will I square it before I'll pass 123?
Oh, no. Not
Seven.
7 times
7, exactly.
27.
So it's enough. It's not exactly, but it's enough to do 7 squaring operations to get to 128. In order to actually get 123, you need to take the binary representation of the number. So it's 2 times 7, worst case. So, and that is important for encryption, because in encryption, you take numbers to the huge powers. The power are like 2 to the power of 4,000. That's like the size of the number you should do. So if you try brute force operations, you will never get there. But if you do this method, this will only take you 4,000 steps to figure out what is a to the power of 2 to the power of 4,000, which are the size of the encryption numbers. So it doesn't really matter here. It was just general knowledge. But I think we all agree that at least for this course, if you get such a problem in the test, you wouldn't like any of the solution I suggested, neither multiplying 123 times or even 7 times or such. So this is the problem I'm presenting, and I come with solutions, right? We will see that using the geometric notation, the answer will be quite simple. And I say this is an algebraic question. It's not a geometrical question. That's what I said before. We use the geometric point of view even to solve algebraic problems. In this case, it doesn't always happen, but in this case, the geometric view helps to solve an algebraic problem. Usually it's vice versa. In this case, that's what's happened. Agreed so far? So I didn't tell you what is the solution. I just promised you that there is one. And I think that's a good time to take our 15 minutes break. Come back and at 2:15, please.
Yeah, just pass.
Okay,
Those taste better.
and we're back. So I promised you before the break that we'll see how the geometric notation will help us and calculate, among other things, calculate a large power of a complex number, and now we will see why. So I'll write that it is an example, but it will sum up to be a theorem. So given two complex numbers of length 1, cis of theta 1 times cis of theta 2, I wish to know the result, okay? And now I have to say what's the problem with the notation of e to the I of theta. If I will write e to the I of theta 1 times, now we're talking about you, times, yeah, look, because you asked me why not to use this notation straight ahead, and I will show you a problem with it. The question I'm asking is, what is the multiplication of two complex numbers? Leave the distance part, the R part, the absolute value part alone. Just the cis, the cosinus and the cosine and I sine. So what is the multiplication of these two? So if we look at this notation,
I think it's the sum.
yeah, it's e to the power of I times theta 1 plus theta 2. Agreed? Does this convince you that this formula is true? Is it true that cis of theta 1 times cis of theta 2 is actually cis of theta 1 plus theta 2? Because here, what law did we use to do this? Laws of powers of numbers, right? But do you actually believe that e to the power of I theta is cosine theta plus I sine theta? It is true, to be honest, but you don't know why, right? So in a certain sense, it is a good notation because it gives you this law which is actually true, but it feels like cheating, right? So now we'll do it, we'll prove that it's true. It is true, but we'll prove it in a convincing manner, okay? So it's good to remember using that law sorry. It's good to remember the law I'm about to prove using the notation of e to the I theta, but not to convince anyone that it's actually a mathematical truth. So, what is the product of cis theta 1 and cis theta 2? So first of all, what does cis theta 1 means? It's the cosine of theta 1 plus I times the sine of theta 1, right? Times cosine of theta 2 plus I times sine of theta 2. Do you agree so far with what I've written? Now, how can I calculate it further? What is the next step?
The distributive.
The distribution law. So it's cosine of theta 1 times cosine of theta 2, right? Minus sine of theta 1 times sine of theta 2. Where did the minus come from?
I.
That's the I squared here, right? It's I sine of theta 1 times I sine of theta 2. I squared is -1, so this is what we are left with. This should remind you of the convoluted multiplication AC minus BD. Again, we see it again, and now with all its glory. Why? Can anyone recognize this formula? Yes?
Oh wait, yeah, isn't it the
Double sine law?
yeah. No, it's cos 2 theta. No,
Not
it's the
exactly.
cos theta 1 plus theta.
Yeah, it's the cosine of the sum of the angles, which is exactly what I hinted at, that it's the cis of the sum of the angles, like we saw in the e to the I theta notation. It's actually true. That means that the multiplication of complex numbers is easily explained geometrically. It's just the addition of the angles. And the convoluted algebraic formula is actually the formula for the cosine of sum of angles and the sine of sum of angles. I will write the formula until its end, but that's the exciting part, in my opinion. So we add I times, and what does I is multiplied by, or multiplies? So cosine of theta 1 times sine of theta 2 plus sine of theta 1 times cosine of theta 2. Can anyone recognize this formula?
I forgot all my identities.
It's the sine.
Yeah, so let's
Sine
trig identities. That's not yet. Yay. These. Right, you see, cosine of alpha plus beta is cosine alpha cosine beta minus. That's where the minus come from. The I squared equals -1 is due to this little negative number here, minus sine, and the sine of the alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. This is exactly what we have here. Cosine minus sine, and cosine sine plus sine cosine. I will copy it so you will have it. See? Remember. Therefore, all we have here is a cosine of theta 1 plus you should know plus theta 2 plus I times not you I times sine of theta 1 plus theta 2. And if you look from the start of the argument to its end, that's cis of theta 1 times cis of theta 2. And how can you, what do you call this in shorthand? That's the cis of theta 1 plus theta 2. And I'll write it in a few seconds in a theorem, but that is what we found. Any questions so far?
Do we remember of these identities by heart?
Yes, the sine of the sum, these are the main to remember. The sine of sum of angles and the cosine of sum of angles. These are the main that will help you throughout the courses, not just linear algebra. Yeah, sure. And I don't even need the alpha minus beta because you need to remember that sine of negative beta is negative sine of beta, right? Because sine is an odd function and cosine is an even function. By the way, for whoever doesn't remember sine and cosine at all, I will define them at the calculus class. But we went through the rough parts anyway. So the theorem is conclusion R1 cis theta 1 times R2 cis theta 2 is actually R1 times R2 times cis of what is the new angle?
Theta 1 plus theta.
Theta 1 plus theta 2. Okay, that's the beautiful way to look at the multiplication of complex numbers using the geometry. And one might say this is the actual multiplication, and the convoluted algebraic multiplication we did last time is just due to this fact. And the AD minus AC minus BD is actually the formula for cosine, and the AC plus BD, AD plus BC is the formula for the sine of the sum of the angles. For example, many children ask, even big children, many children ask why is negative times negative is positive, right? It's a valid question. Why, when we multiply two negative numbers, do we get a positive number? So there are a few answers to this, but I think the most accurate mathematical one is because the number system we use is actually part of the complex numbers. And what is the angle? The angle of a negative number, right? Even if we have only the straight real line, then what is the angle of the positive numbers? 0, right? What is the angle of the negative numbers, the numbers here? What is their angle? How much? Pi or 180, right? Because we measured from the positive side. So the angle would be 180 or pi, right? So the answer, pi. So if we multiply two negative numbers, what is the angle of the product of two negative numbers? So one negative number, its angle is pi. The second negative number, its angle is also pi. And we know that the multiplication sums up the different angles. So pi plus pi. So what is the new angle? Yeah. Pi plus pi, which is 2 pi, which is equivalent which is equivalent to 0, right? And you get back to the positive numbers. And you also get I now, because I, what is the angle of I? What is the angle of I, the complex number I? Half a pi. So what is the angle? What is the angle of I times I squared? Pi, because it's 2 times half a pi. So it's 90 degrees plus 90 degrees. That is 180. And that is a negative real number. Okay, so the positive is the angle 0, the negative is the angle pi. And therefore we see all of the properties we already knew and some new properties as well. And these are the actual numbers that surrounds us in the real world. Any questions so far? So now the Moavel, I'm not sure how to write it in English.
I.
In its general, in its original, sorry.
Yeah.
That's the Moavel?
Pretty sure, yeah.
That's, נניח. The Moaver law is pretty easy. Why? If we have R cis theta and we take it to the power of n, what does it equal? So it basically means multiply this number by itself n times. What will happen to the absolute value, to the distance r? It will be r times r times r, and altogether, what will it be? R to the n. But what will happen to the angle? Because theta plus theta plus theta, so what will be the new angle? N times theta. So that is the Moavel law, but it's an easy conclusion from the fact that the product of two complex numbers is just the addition of the angle, the product of the distance, addition of the angle.
When talking about the angle, do we say the angle is n theta modulo 2 pi or?
Yeah, but you don't have to say, that's what cosine does.
Mm.
It fixes it. Because because what I said it derives exactly from the formulas above. It's actually n times theta. The fact that you can take the modulo over two a whole times of 2 pi, the whole number integer number time 2 pi, that's because cosine and sine are periodic. Okay. So before I showed the Moaver, I want to give another example. I should have written it before the Moaver, but I was excited. So let's look at the following example. Take 1 plus I, which I've shown you before, call it Z1, and Z2 would be square root of 3 plus I. Let's put it before the Moaver, sorry. I'll write it here, the Moaver, because, and I will write an explanation, because this actually equals R times R times R times cis of theta times cis of theta. You're all right. And times because I only explain by heart, Belche. and I didn't write it, so I hope this will help you remember 10 times. Okay. I'll give you a minute to sort out your notebooks, and then I'll go back to the example. Are you showing me mathematical means? Okay. So let's go back to the example. And the reason I also switch places with the mover is because I actually want to spend some time with this example to show you a few things. So I wish to calculate Z1 times Z2. I will do it twice, once in the algebraic notation and once in the geometric notation. It will also help us to remember how to convert from one version to the other, and also say that it's the same, these are the same complex numbers. These are different point of views, but of the same system. Okay, so let's start algebraically. I'll write something of what I just said. We will calculate, we will calculate their product, both algebraically and geometrically, both. Okay, this is redundant. I don't need to usually do it twice, but I will wish to show you that it ends up at the same place. Okay, so first algebraically, what is Z1 times Z2? So it's 1 plus I times the square root of 3 plus I, which equals the square root of 3 minus 1, that's the I squared, plus I times the square root of 3 plus I times plus I. So that is the number altogether, square root of 3 minus 1 plus I times the square root of 3 plus 1. Agreed? Now we convert all numbers to their geometric form. This is not even my final form. Okay. Okay. So Z1 we already did, was square root of 2 sine of pi over 4. Z2 was 2 times this of pi over 6. Not 60, 6. And their product is the so-called new number. And we'll do it together. So for the last and third and last, for the third and last number, the product. And first of all, how do you calculate the R, the distance, the absolute value?
2 times. Yeah, 2 times the square.
It's not 2 times because it's a different number. It's the square root. I'll write the formula here. So it's the square root of 3 minus 1 squared plus the square root of 3 plus 1 squared. Agreed? Can anyone who follows the lesson guess what will be the answer after I simplify it?
3? No.
No, not at all.
Not following close enough.
Yes, because this is what is this number? It's the product of these two numbers. And I told you, when you multiply two complex numbers, the new distance is 2 square root of 2. So here will be the square root of 8.
When I said it, you said it wasn't that.
What?
When I said it, you said it wasn't that.
You said 3.
No, I said that before. It's 2 times the square root, and it's like, no, it's a new number. It's like, okay, this wasn't that.
Ah, no. But we're calculating it. We're not
Ah,
guessing.
no.
We wanted to convert this number to the geometric form. Yeah.
Where do we get the geometric forms for C1 and C2?
We did it earlier in the class, so I just did it quickly. Right? I didn't even do it quickly. I just told you we did it beforehand. But you were supposed to do the same thing that we do here 3 times. I won't do it. I do it just once. And these two were examples from before the break.
Yeah,
Okay.
the square root of 8, which is
Yes. So this is supposed to be. Let's make sure that it's true. It's the square root of 3 minus 2 times square root of 3 plus 1 plus 3 plus 2 times the square root of 3 plus 1, which is, surprisingly enough, the square root of 8, which is 2 times the square root of 2. And it's not surprising. That's what we are supposed to get, right? Because the distance of z1 times z2 is supposed to be the product of the distances of the absolute values of z1 and z2. What about the new angle? What is supposed to be the angle of this number?
4 plus 5 over 6.
The sum of the angle. It is supposed to be pi over 4 plus pi over 6, which is something.
5
And
divided by
12, it's by 12, right?
Five
It's
pi
3
divided by 12.
plus 2, right? It's 5 over 12 pi. So let's make sure that that's actually what happens. And I'll remind you, how do we find the angle?
dark down.
First, we need to see if the real part is positive or not, or negative. The square root of 3 minus 1, is this a positive or a negative number? Positive, it's a square root of 3, it's more than 1,
Ah, right.
right? So, since the square root of 3 minus 1 is positive, then theta, the angle, is just arctan without the plus pi of the imaginary part over the real part. And now we use the calculator to get 5 over 12 pi, surely. Let's hope for the best. Oh, that's not fine. We need 4 prime. It's funny, it doesn't give it in radians. It's 75 degrees. Is that 5 over 12 of pi?
That's a
Oh, here it's for it. Yeah. 5 over 12 of pi. Yay. Okay. Yeah, I think 45 plus 30 is a bit easier in degrees, right? Because the pi over 4 was 45 degrees and the pi over 6 was 30 degrees, and the summation is 75 degrees. But for us, radians are the way to go. So it's 5 over 12 pi, which is exactly, not surprisingly, pi over 6 of pi over 4. So I hope I convince you using this example that these are not 2 different words, the algebraic one and the geometric one, but 2 different ways of looking at the same word and world and calculating the same things, and we always end up with the same results. whichever way we do. And it's, I think it's obvious that if I'll ask you to multiply two complex numbers, it will be much easier in the geometric form than the algebraic one. And I will do it, another example like that later with the power of 123. Yes.
I think I asked already, but I didn't get the full answer. But what happens if the angle is in the second quadrant? Because we said like
Plus
if
pi.
plus pi
Yes.
from
Because the real part is negative. Because arctan give you angles in the first quadrant or the fourth.
yeah.
So the second is the negative of the fourth.
Yeah.
So you add plus pi and you get the right angle. Because the arctan will the shift tangents will return to you a negative angle. And when you add the plus pi, you'll get something less than pi in the second quadrant. Okay. Okay, so that's the Moivre law. When I take a complex number to the power of n, I get this. And now I can say, I can give you the example I wrote before. What is 1 plus I to the power of 123? So first of all, we will convert the number to its geometrical form. Why? Because it's much easier to answer the question in the geometrical point of view. And again, I'll remind you that we already know the geometric form of this number is the square root of 2 times cis of pi over 4. Green. And that's to the power of 123. So the absolute value, the distance of the number, is simply square root of 2 to the power of 123, and have a lot to do with it. I can write it's 2 to the power of 61.5, right? Nothing more than that. But what's really interesting is what happens to the angle. So what happens to the angle? It's multiplied by the power. And now I can take the modulo of 2 pi. So how can I simplify it further? So like I said, that's 2 times to the power of 61.5. Or 2 times to the power of 61 times square root of 2 times. And now what do I do with the cis? So 120 times over 4 is 30. So it's 30 pi plus 3/4 of a pi. Do you agree? Because 123 is 120 plus 3. 120 over 4 is 30 plus 3/4 of a pi. And what is actually 30? It's 15 times 2 pi. So what does both cosine and sine do when you add an integer number of the whole circles? It erases it, because that's the periodic of cosine and sine. So we are left with 2 to the power of 61 times square root of 2 times cis of 3/4 pi. And first of all, that's the answer. That's the final answer. But let's use Wolfram to. I'll write the first step. I wish to return it to an algebraic form, and then I will use Wolfram. So it's time cosine of 3/4 of a pi plus I times sine of 3/4 of a pi. Let's see if we can easily find out these values. Second, so cosine is 0, then it's sorry,
1 0.
cosine at 0 is 1, and then when another no, it's quarters, not halves. Sorry. What I wanted to say is false. I used Wolfram. I thought 3 halves, not 3/4. So let's use Wolfram. So it's minus plus. Okay. So that's times minus 1 over square root of 2. Oh, it's nice. Plus I over square root of 2. Why did I say it's nice? Because the square root of 2 cancels. And we get all together 2 to the power of 61 times I minus 1. That's nice, right? That's easy enough. And in a few seconds, we will check for any mistakes. But this is supposedly the 123rd power of 1 plus I, which was done in less than 123 steps. I'm not sure if it's less than 7 steps. No, I think it's also less than 7 steps. Okay, so let's check Wolfram. So on the one hand, I will tell him 1 plus I to the power of 123. Let's see what it says. Yes, so it's this huge number in -1 plus this huge number. So what do we hope for this huge number to be? 2 to the power of 61. And if it doesn't admit it by itself, okay, I'll open another tab of Wolfram, and I ask him 2 to the power of 61. And wow, even I didn't believe it. The first few numbers seems right? 2305, 2305. Yay. Okay, so we actually found the right number. Okay. Any questions so far? And lastly, think lastly for the complex numbers. And now we wish to study roots of complex numbers. For example, what is the third root of 1? What will your answer be? If someone tells you, please find the third root of R, what would you answer?
R of 1.
Of 1, 1, sorry.
1, it's 1, right?
You would say 1, right? 1. But now I'll ask something a bit different. How many, because it's italic, I found it in my head. Oh, now my neck is much better. How many solutions does the equation x to the power of 3 equal 1 have? What is your answer to that? Do you see the connection between the two, right? When I ask a third root is what to the power of 3 returns 1, right?
1.
So you would say 1. And reminder, we study complex numbers. So I'm asking how many complex solutions So you say 3. What are the 3 complex numbers that cubed equals 1?
1 0, and then I have no idea, but I'm gonna
Or-
assume that it's.
You can give
that
me
it's-
the geometrical form of the solution.
Third
This
root,
triangle.
third root of 1 cosine x
triangle is not what I was looking for. The geometrical notation is distance and angle.
It's is it -1 and 1 and -1 and -1?
No, it's.
I mean
is it-
-1 and I and -1 and -9.
No,
Is it,
no.
is it
But you can give me the geometry. If you
Is it-
can actually see it, give me the geometrical.
the third root of 1 and 1/3 of 2 pi?
The third root of 1 is 1. So
No, I mean, yeah, so the
So so you say the distance is 1 and the angle
is 1/3 of 2 pi.
1/3 of 2 pi. In degrees, how much is that?
360 divided by 3, 120.
120, and it's true. Okay. So if we take cis of 120 degrees when cubed by the Moivre law for multiplication of complex numbers, which is the same, it's the cis of 360. And what is the cis of 360? 1. Can you think of another number when cubed gives you back 1? Before we continue, let's look at this result, okay? So what is cis of 2/3 of a pi? Again, I don't like for you to think it's magic. It's actually the complex number. So I know how to go to the algebraic form. That's the cosine of 2/3 of a pi plus I times sine of 2/3 of a pi, which equals, I know about, but not exactly. I think it's -1/2, but I'm not sure. And square root of 3/2. Yes, correct. Okay. So it's -1/2 plus the square root of 3/2i. So it's a specific complex number. What will happen if we take this number to the power of 3? Can anyone guess how much that will equal?
It's -1a.
The answer is 1.
Yeah, of course. It's going to
Because
be
no,
one.
okay, that's what I wanted to make sure. You're saying what I'm saying. We'll show that it is, but that's what I'm claiming. I wrote, that's why I say it looks like magic, right? Because it looks like it has nothing to do with what I did before, but it does. I'm claiming that according to the Moivre law, cis 120 degrees cubed is equal to 1. Now I'm doing the very same calculation in the algebraic form. It must equal 1, right? But let's see, it happens. So remember that a plus b cubed is a cubed plus 3 times a squared b plus 3 times a b squared plus b cubed. Okay, so let's use it. So the first thing is -8 plus 3 times a squared is quarter times the square root of 3/2i plus, which will be minus 3 times half times the square root of 3/2i squared. Allergic to the complex number.
We all are.
Yeah, right. That's the easy part of the course also. Okay. Cube. Really, Thomas, how didn't you see that?
What? Ah, that it was one.
Easily. No, yes. How do you not see now that it's one? It's so obvious. Okay.
Obvious, yeah.
Yeah. Okay. So that's further simplified. I like that I said further simplified as if we simplified it some more. So it's minus 1/8. That's simple enough. And here we have plus 3 times the square root of 3 over 8 times I. Agreed? What happens here? I squared is actually minus 1. It cancels out this minus, so we get plus. And what is the squared? So in the denominator, 2 squared is 4 times 2 is 4. 8, sorry, 4 times 2 is 8. And square root of 3 squared is 3 times this 3. What do we have in the numerator? No one followed the calculation?
9.
Yes. I thought you say no, but yeah. 9.
No, but yes.
It looks German, right? Okay. So it's 9 over 8. And lastly,
Is it negative?
no, it's
Positive.
close because I squared is
Yeah.
minus 1. Lastly, what is the square root of 3 cubed? Square root of 3, square root of 3, that's 3 times square root of 3. So it's plus 3 times the square root of 3 over 8 I cubed. What is I cubed? Yeah, because it's I times I, which is negative 1 minus I. And you can notice that this and this cancel out. And we're left with 9/8 minus 1/8. And what is it all equal together? 1, yay. Okay, so again, this is for the geometric notation. It was a bit easier, but to convince you, it's not magic. It's the same thing using laws that makes it much easier to work with. Okay, and now I keep asking you, can you find another number
Is it
that cubed equals 1?
4/3 pi? I think that's fine.
4/3? Yeah, I think you're right. So 4/3 of pi is 240 degrees. And why does it work? It's obviously not 360 over 3, but 360 over 3, there is only one answer for that. But what happens when you take 240 and multiply it by 3? What do you get? You get 3, so 720. But what is 720? If not 2 times 360, it's not 0. It's the same thing, right? So we got 3 different solutions for the cube. And I will write that cis 240 degrees is actually half, negative half, minus square root of 3 over 2. Don't worry, I'm not going to verify that's cubed equals 1. I will put in Wolfram alpha to be sure that I'm not mistaken. Yes, I'm not. So we found 3 third roots of 1, y3, I mentioned 2, but the first one is obvious, it's 1 by itself, right? So it's 1 and negative half plus or minus the square root of 3 over 2i. And is it a coincidence that we find 3 distinct roots? Are there any more? So, general theorem.
There's a root there.
Given a complex number which is not 0, are this theta. Let's see. And given a natural number n, the equation z to the n equals r cis theta has exactly n distinct solutions which are given by the following formula, dk equal this nth root of r times cis of theta over n plus 2 pi times k over n. So we will prove it in a few. I'll show you an example before, but that's the theorem. There are exactly n distinct roots for any complex number, which is not 0. Why? Because for 0 there is only one solution, 0 to the power of n. But if you take any other number, any other complex or real number, it has exactly n different roots, which is quite different than the real numbers. In the real numbers, you have at most 2 different roots. And usually it depends if the power is odd or even, but never more than 2. It's either 1 or 2. The complex number is always n distinct ones. Any questions up till now?
Why?
By the way, to answer why is this formula correct, it's quite easy. Look, take this formula and take it to the power of n, raise it to the power of n. What is the square root of n of r when you raise it to the power of n? That's just r. And what happened to the angle? It is multiplied by n. So the n cancels out and you get theta and a whole number of whole circles, full circles, right? So it's quite obvious why is this formula correct. I will show you how to get to it any case, and it still doesn't answer why there are exactly n distinct numbers. And also I forgot something. What do you substitute for k? So k, you can substitute 0, 1, 2, and all the way up to n minus 1. Okay, these are n distinct variables. And I will explain to you in a bit why these are exactly, why are these the solution and why are they distinct, and are there no others? I will explain all this in a few, but first of all, I want you to see that we can actually use it to do calculations. So example, we'll start with an example, not with a proof. Give me any complex number as an example. Choose a complex number.
3 plus 4i.
Someone else choose a complex number. One of the examples we did, so it won't be too ugly to calculate the angle. So one of the examples we did. Do you remember any of the examples we did?
Absolutely no idea.
One plus I.
Okay, so square root of 3 plus I. Great. Okay, so this is the number 3, and we wish to find roots of it. Choose any natural number.
No.
Yeah, so find 100 distinct roots. So anyway,
Anybody here is 4, 4.
the first row is a bit problematic. I don't include her with you guys. And any small natural number?
4, just
4. Okay,
4
great.
words.
So there's supposed to be 4 distinct complex numbers when raised to the power of 4 will equal exactly the square root of 3 plus I. And how do we calculate them? We simply substitute into the formula above. However, you should notice that the formula above uses the geometric notation. So the first step I should do when answering such a question is solved, right? Is to convert the number from algebraic notation to the geometric one. So first, we change to the geometric form. So z to the 4 equals geometric form was 2 times c, so pi over 6. That's why I wanted an example that we had before. I don't need to calculate the geometric form. Okay, so therefore, the 4 distinct solutions are, listen closely, zk equals, and I will actually copy the formula here and substitute each value that I know. What is n, for instance? What is the value of n in this example?
4.
Yeah, it's the power here, it's 4. So instead of n, I'm substituting 4 into the formula. Next, what is r?
4, 2.
2. That's the value here, right? Look at the formula again. Now look at me. Z to the n, how many solutions does this to the n equals RC state ahead? So the n is the power here. The r is the distance of the number for which you wish to calculate its roots. And the theta is its angle. So the n is 4, the r is 2, and what is the theta here?
The same, right? Pi over 6.
Pi over 6. Okay. I feel that's because the formula is מסובכת, then you are fearful to even substitute into it, but you shouldn't be, right? That's the formula. All we need to do, given the example, is substitute it in the given numbers, the given data. So that's the solution, and I'll give you another chance to answer other than Thomas. What are the values of k? What are the different values of k we should put in this example?
0.
0, 1, 2, 3, exactly, because the n is 4. So k is 0, 1, 2, and 3. So we have 4 distinct solutions. Z0, when k equals 0, is the fourth root of 2 cis pi over 24. And Z1 is almost the same, but what do I add to the angle here?
Zero.
No, 0 was before when the k was 0. Now the k is 1.
Oh, that's what's going on.
So here we put a half of pi. Yes. And next, Z2 is the same thing with 3/2 of a pi. No, with pi, 2/2 of a pi. And lastly, Z3 is the same thing plus 3/2 of a pi. So these are the 4 different solutions. And let's use Wolfram alpha to verify one of them. Let's just take, for the sake of our argument, Z2. So I use Wolfram to convert it to its algebraic form. Not particularly nice. I don't see any easy way to write it. Let's try to copy the first 3 digits after the decimal points. So it's minus 1.179 plus 0.155 I. It's not exactly the number, but it's close enough. And supposedly, if I cubed, take this to the power of 3, what do you expect us to obtain? Not power of 3, I'm sorry, the power of 4. What do you expect us to obtain?
Do radical 3 plus I.
Yes, to the power of 4, let's ask it. It will be about, it won't be perfect. So you see the 0.998 is close enough to 1 because we're supposed to get I, and 1.732 is supposed to be close to the square root of 3, radical 3, square root of 3.
1.7 something.
Yeah, 1.73. So you see it's actually true. That's not a proof because I took approximation, but again, it's just to convince you that something real is happening here. And the same goes for every other root here. So we found 4 distinct root of the square root of 3 plus I. Let's do another example. And
Sorry, just
Yes.
to be clear, why does it have to be exactly?
I didn't prove it.
No, I know, but my question goes towards when you look at the formula, it's
That's the
K.
proof, Thomas. That's the proof. Within the proof, I will convince you these are n distinct roots. Okay, I want first for you to have examples in the hand, and then I will prove why it's generally the case. Okay, so example. Now solve z to the 5 equals I. Okay, I want the 5 distinct fifth roots of I. So first I convert I change it to its geometrical form. What is the geometrical form of I? What is its distance from the origin? 1. And what is its angle?
This half pi.
Half of pi, right? I is on the y-axis, and on the positive side, the angle is a straight angle, pi over 2. Now we simply substitute into the formula. And now, whoever didn't answer before, try to see that you know what every element of the formula means. So let's start with the k this time. What is the range of k between what and what? 0, 1, 2, 3, 4. Exactly. Now, what is the n in this example? 5. So everywhere where it's written n, I substitute 5. What is the r here? 1. That's the distance, the absolute value of the number which we calculate its roots. And lastly, what is the theta? Pi over 2. And that's it. You just need to plug in 5 different k's and you'll get 5 different answers. Again, let's try one of them just for the sake of example. Z3. So what is Z3? This 5th root of 1 is 1, so I don't have to write it. It's the cis of 1/10 of a pi plus 6 pi over 5. And I claim that this number, when raised to the power of 5, give you exactly I. Let's use Wolfram. So this number, the power of 5, now it will be exact. So I gave him the exact form and he gave me an approximation. It's a very good approximation, I must admit, because it's 1.00000000000 and so forth. Yeah, the answer is I. I don't know why you just say I. Funny. Yeah, expanded form. I. Why is it? Why is this the expanded form? That is the simplified form. Okay. Has to do with its algorithms, I guess. But the answer is obviously I. Okay, so we know how to calculate roots. And remember that it's roots of complex numbers, but it's also roots of real numbers. The answers are usually complex, but you can find, let's do one last example, okay? Example, the square root, the 4th root of 1. Example, and solve.
Now, wouldn't it be more interesting to get a root that exists? So like
No, but exists always the two rational and the two real options.
no, but like
it will never be surprising.
I mean, yeah, but like if you say like you
So there are roots, so that's what happens. 2 roots of this equation, you know, which 2 solution for this equation, it does contain what you wanted. What 2 solutions to Z4 equal 1 do you know?
-1 and 1.
Yes, so obviously -1 and 1 will be 2 of the answers, and you'll get 2 more. That's exactly what will happen.
I was thinking like the cube root of 27 or something, but okay.
Yeah, it's the same. So we'll change to the geometric notation. 1 is actually the cis of 0. The angle of a positive real number is 0. And therefore, zk, the solutions are the fourth root of 1, which is the absolute value of the original number, times cis of the original angle, which is 0 over 4, plus 2 pi times k over 4. And we get z0 is cis 0 is 1. z1 is cis of what? If k equals 1, what is the angle we are left with? Half of pi. Who is cis of half of pi? I. And think about it. What is I to the power of 4? It's I squared times I squared minus 1 times minus 1. It's 1. That's true. Z2 is cis of what is the angle here?
Pi, which is -1.
Pi, which is -1. Z3 is cis of 3 pi over 2, which is negative I, which also to the power of 4 equals 1. So I like this example because one can see easily that we find true solutions to the equation without any complicated algebra. Any questions so far? So I think I got you to the brinks today. So we'll finish now. Next session. When is next session?
In a week.
Not necessarily. No, in a week there will be one.
And the beta.
Okay, great. No, because I'm flying to London and Glasgow 2 days into the semester, but it's Sunday and Monday, not Tuesday. Tuesday is already Pesach.
So if we will.
Oh, right. Yes, yes. I will tell you about it, but yeah, one meeting of Infi will be canceled. Yeah, in any case, next week we have a lesson as usual. We will prove these are to this formula, this theorem, and then we'll move on to linear sets of equation and matrices. We'll start linear algebra. This is not real linear algebra. This is just, I don't know, numbers. It's important for linear algebra, but it's just the numbers, right? And then we'll start doing a linear algebra. But not to be confused, I will ask a question about it in the test, right? Whether it's called linear algebra or not, you're supposed to understand it for this course and for others. And I'll see you in a bit in calculus, most of you.
This reminded me.
Stop using complex numbers.
We actually end up proving
Now we prove it next time.